Today we're going to be uh, working some physics problems related to work. We're going to be basically more or less motivating a lot of ideas. We're going to be doing less of the. We're not going to be doing any number crunching actually with someone pulls a box up a ramp, how much work is done from here to here. That's kind of a trivial thing. You can really learn anywhere how to do that. You see the problem process once, and you kind of got it. So I don't think it's worth spending time on. So we're going to be motivating a lot of ideas, so the calculations become more intuitive, which I think is a lot more important than number crunching. Um, and it also helps you get a better conceptual understanding, which is what the AP exam is going to ask you for, anyways. So let's get the idea of work being motivated. So everyone sort of has a vague idea of what energy is. If you think about, let's say, a man, a very poorly drawn man. Let's say he's pulling a box, and here's his string that he's using. So, and he's pulling the box with some known energy, some known constant energy, or may be constant, may not be constant, and some known force. So the whole idea here is we want to construct a quantity that can directly measure the amount of energy expended by the process of him moving that box. And the whole idea is that we want to um, construct it over distance, right? Because the longer the man pulls that thing, or man or woman, the longer he or she pulls the box with that string, the more force they're gonna have to use, or the more energy they're gonna have to expend. So this travels from one distance to another distance. We'll call that delta x, and we'll say we know this angle, theta. So we're gonna talk about trig functions real quick, and it's gonna be a little hand wavy because you probably don't know vector identities if you're in AP Physics 1, because that's normally a Calc 3 topic or a Physics C topic, depending on which one you take first. So, oh, and another side note, I would be doing like tangible problems, but again, there's no one here to like talk about the Q&A and ask me questions for the Q&A, so we have a lot of time on our hands. So we're going to think about some trig functions, and I'm just going to graph them for you, the two main trig functions. This is almost a full period of cosine. We'll make it a full period, actually. So this is y, this is x, and this graph is y equals cosine x. If you don't know how to graph it, just believe me. So we do see that this cosine graph is a maximum at 0 angle. And graphing sine, we'll see that it's a maximum. You might know, you don't have to believe me. Or you do have to believe me, but you don't have to know. It's y equals sine x. And that's at a maximum at 90 degrees. So the whole idea is that, oh, hi, we just had someone join the stream. Hi, Ari. Basically, we're just motivating the idea of work right now and the equation for work, given the force and distance and an angle. So the whole idea here is that we know that work is going to be, well, if the person is exerting more force, they're going to be expending more energy. So it's proportional to force. And the longer they the pull the box, the more work they're going to output because the more energy they expend. That should be intuitive. So we know it's proportional to that, but we have to think about the factor. We have to think about some other factor, because if the person pulls the string directly upwards while walking backwards, they're not going to be moving the box at all. So we have to think about what happens when the angle is 0. When the angle is 0, um, the force is doing the most work, right? It's the easiest to pull it. So that angle 0 would mean it would be at a maximum value. The work would be at a maximum value given a force. And for the opposite case, at 90 degrees, you wouldn't be performing any work. And this isn't right, I don't think. Yeah, this isn't. Sine of 90 degrees. No, sine of 90 degrees is one. Okay, so yeah, so at 0 degrees, this would just be that value. So for some vector identity reasons, we tack on a cosine theta here. I wish I could better explain it. Basically, the whole point is that we tack a cosine theta onto one of those values. So if we rewrite this as f cosine theta delta x, and we draw out the vectors, we have this going this way. It's going this way. There's an angle theta between them. That's f. That's delta x. The component in the delta x direction would be f cosine theta, right? Because we have a badly drawn component diagram. That's f. That's f in the direction of delta x. Cosine theta is equal to adjacent over hypotenuse, which is f in the delta x direction over f. So we have f in the delta x direction is equal to f cosine theta. You can do the same thing with the delta x and find delta x in the f direction, but that's a little less intuitive. So that's why that is there. The things it gets a little wonky when you're talking about a non-constant force, in which case you have to use some calculus to solve the problem. But yeah, so that's our idea, and we're gonna sort of brush on the calculus a little here and talk more conceptually about it. So what if we have a non-constant force? More specifically, we'll talk about a linear force. So we have the force is a function of x, and we have a force that increases linearly. So if we think about a way we can approximate the amount of work done, we can assume the force is constant on small intervals, which means that we'll get, let's see, we'll label this x. Well, we'll just use numbers. 1, 2, 3, 4. And let's say this is just f at 1. F at 1. I'm gonna not label the lines because it'll get gory. F at 2, F at 3, and F at 4. So the idea is if we approximate the function as constant over a small interval, we can say that the total work is approximately force 1 times the displacement, which would be 1 minus 0, plus force 2 times 2 minus 1 plus, we'll do it this way actually. We'll say that this is the displacement over the first interval. We'll do delta x sub 1. That matches the notation a little better. F2 delta x sub 2 plus F3 delta x sub 3 plus f sub 4 delta x sub 4. And the idea is we can write out this summation using shorthand notation. We can say this is the sum over all values of k of f sub k delta x sub k. K can be any variable. It's just we're choosing k there because it's not too commonly used in this context unless you're talking about springs, which we might if I'm feeling it. But I'm probably not going to be too exciting just because I'm pretty sick. So the idea here is that as we're gonna, so what should be obvious here is this is the area. This can be an area element of this rectangle right here. And this can also be an area element of this rectangle right here. So we're essentially approximating it as the area. And when we increase these subintervals that we have, I'll draw it quickly just because I don't want to get too deep into this. Let's say we have this, and so on. You notice that it's going to better approximate the area as we increase or decrease the width of those intervals. So although this is an approximation, if we let the individual components, the individual displacements, get infinitesimally small, get very, very small, then this will be exact. And that's what's called the Riemann Sum, and you'll learn about that if you take calculus. So we're gonna motivate something here. There's a neat little proof, or there's a neat little work or a theorem called the work energy theorem, I think it's called. It says the work done by the net force is equal to the change in kinetic energy, which is kind of hand-wavedly proven, really, but not really. So we're gonna talk about this a little bit more. So we've established that these two are exact if we let the displacement go to zero, or get very, very small. So now that we've established that, we can work with this, and we could just substitute indexes in. So then the work done by the net force is going to be equal to the sum over k of f sub k, and instead of putting net in the subscript, we're going to put in the superscript. That doesn't mean it's a power. That just means we're denoting it a different way. F net times delta x sub k. But what is the net force? The net force is just ma, and we're going to assume a constant mass. So we're going to assume constant mass, which means the mass doesn't change. I'll just write delta m equals 0. And we're also going to assume that the initial speed is 0. This is just simplify the calculations a little bit. And then we can extrapolate it to a non-zero initial speed. But what's the net force? We're going to go back to that. The net force is just ma, right? And if m is constant, then eb sub k is also going to be a constant value, so we can just denote that as m. So that'd be m, however the acceleration won't be constant generally. M a sub k delta x sub k, sum over k. And we are going to substitute in an expression for a sub k. And we have the initial speed is 0. So this means, again, the sum over k of m, and a sub k is going to be v sub k over delta t sub k times delta x sub k. So there's a neat little explanation here. When we have the acceleration, when we're talking about the acceleration, we'll talk about this in the next step actually. And then the next thing we're going to do is substitute in another expression for the delta x sub k, v sub k over delta t sub k times delta v sub k delta t sub k. And the reason why we could do that is because displacement is change of speed over change of time. And this right here is significantly different than this. And the reason why is because when we're measuring acceleration and we're going to approximate acceleration, let's say we have some displacement graph like this, or we'll do speed instead. When we have acceleration and we're approximating acceleration, we use the change of speed over the tire interval. But when we're talking about that delta v sub k, say we're taking the graph of, I don't know, kinetic energy versus speed. That'll be a parabola. When we're taking the value of delta v sub k is an interval. So we can't just take delta v sub k to equal v sub k, just because the initial v sub k isn't necessarily 0, even though the initial speed itself is 0, because the initial speed and delta v sub k, or the initial v sub k and the initial speed, are two different quantities. So we can do some cancellations here. We can cancel the delta t sub k. And we know to do that because we have no time dependence in this entire problem. So it makes sense that we want to get rid of the delta t's. So now we have, sorry, checking my mic was on because it's been acting weird. M V sub k, delta V sub k. And what's MV? MV is momentum. So that's P sub k, the momentum at the kth interval, times delta V sub k. So what do we mean by this initial summation? We meant the area under a curve, right? Because as those rectangles get smaller and smaller, it approaches the area under that curve. So, in the same reason that this one right here represented the area under um, an F versus X graph, a force versus displacement graph, this summation represents the area under a P versus V graph. And classically, P equals mv. There's a reason why we replaced it here. P equals mv, which means that P and V are going to be linear to each other. So the graph will look like this with slope m. And we know how to find the area of this. The area of this is just going to be the area of a triangle. So we'll call this VF. And we'll call this, I'll make that a dotted line. So we'll call this value VF and this value PI or PF. And this is where the initial speed and the initial momentum would come in, because we'd have to subtract the area of two things. But we don't have to deal with that. We could just trust our intuition. So I'm going to move that over here. And what's the area? This is 1/2 base times height. So area is 1/2 base times height. So that'd be 1/2 PFVF. And at this point, it's a little more useful to substitute in the expression for momentum. So it's 1/2 MVF times VF. And now we have 1/2 MVF squared. So work done by the net force is equal to that. And now we've proven that. Albeit a little hand-wavedly, we can just include another term for the initial kinetic energy, and that would just be, well, first off, we need to actually establish this is kinetic energy. This is just a final kinetic energy by definition. The definition we have is kinetic energy is equal to 1/2 mv squared. So we have this identity here that becomes very useful. So what we do to extrapolate to this, or from this, is just add another term. So without the initial speed being 0, we have work net is the final kinetic energy minus the initial kinetic energy. Because in the case where V0 was 0, like initial kinetic energy is 0, which is why it didn't show up in our calculation. So this is 1/2 MVF squared minus 1/2 MVI squared. You also might see it written as 1/2 MVF squared minus VI squared. Make that 2 a little better. But all those are valid. So that's really that idea, which is very important, and it makes you do a lot of things. And we can talk about we can use the argument of energy conservation. And the argument of energy conservation is that we have the initial energy equaling the final energy. And in this case, we have some initial kinetic energy plus some initial potential energy, we'll call it U, equals the final kinetic energy plus the final potential energy. and the potential energy includes all conservative forces there. And I'm not sure if conservative forces have been defined on our streams yet, but a conservative force is basically a force that does zero work if you do a full loop. But that's not important for physics 1. So we can rearrange some terms, and we get ui minus uf equals the change in kinetic energy, kef minus kei. This is basically just negative delta u equals kef kei, and this is actually how a force is defined. How a force is defined is you have some potential energy, or that's how a force is more rigorously defined. You have some potential energy and maybe it looks like this, and then it has some tangent slope like that. We'll say this is u as a function of x. And there's some tangent slope right there, and the force is equal to negative slope. And that's just negative delta u over delta x. So this is negative f delta x. Or rather, it's just f delta x, right? Because that slope is negative and the negative signs cancel out. F delta x is equal to ke f minus kei. We'll just say there's changing kinetic energy for now. Or not for now, just in general. We'll say changing kinetic energy to simplify the writing. And the reason why there's no net tagged onto this is because potential energies are additive, meaning if you have like a planet here and a planet here, their potential energies are going to add together. So the terms will add together. So this is actually the total change of potential energy from all the forces going on around it. So it's just the network. In case you didn't believe the first calculation, now here's the second one. Hopefully you believe me now. So we have two reasons that the network is equal change in kinetic energy. Um, one's a little mathematically heavy and a little more satisfying. And one's definitely not as, I wouldn't say as hand wavy, but it's a lot more intuitive to understand. And the first example is probably much easier to understand if you understand calculus, because we essentially just did calculus. Um, the thing that made us luck out was that the p versus v graph was linear, but if it weren't linear, if it were like p equals v squared, then we'd have to do some sorry, we have to do some special work that you don't have to worry about right now. So we're gonna be talking about. I'm sorry, I am incredibly congested. We're gonna be talking about a little topic. We're gonna say we have this hill or we have this cliff, and there's a man on that cliff, uh, holding a box off the cliff. He has a really long arm, just absurdly long, just an abomination. Um, and he's holding a box. We're gonna make that a little more square. This is now my drawing challenge. That's good enough. So what work is he doing on the box if he just holds the box up? The answer is zero. And that's kind of unintuitive from a work standpoint. From thinking work is a measure of how much energy you're outputting when you're doing something. And albeit that definition is a little anthropomorphized, which means turning something into or humanizing something when it shouldn't be humanized in the first place. It's really common in or it's a common term in like primatology and stuff like that. But that's different. That's a completely different topic, actually. Primatology and like animal psychology. But this work idea isn't just central to like humans. You are expending energy when you're holding that box up. Don't get me wrong. Like I'm not going to tell you that like you think you're expending energy and you're not, because like that'll just mess that'll mess your entire intuition about everything, and B, it's just not true. Um, so there's a very surface level reason why the work here is 0, and the surface level reason is that it's not moving, so delta x equals 0. Therefore, work is equal to 0. Right, because we established work is f delta x times the cosine of the angle between them, and that's always 0, no matter what f or cosine theta are, because it's just going to be a number multiplied by 0. However, your this is more philosophical than anything else, but it's not necessarily your muscles doing work. Your muscles do have to contract. What's basically happening is you have motor units on your muscles, and the motor units are they're doing their neuron thing. Um, so their motor neuron thing. So we have like a let's see a dendrite like this, and there's some ion channels here, and there's all these bunch of ions in here. There's like sodium, potassium, chloride, maybe I'm not sure. But basically, what happens with this is a neurotransmitter leaves here and binds onto the dendrite, and what happens is the gates actually open. Let's see if I can draw this correctly or draw it well. The gates open sufficiently so that the ions can pass through, and that creates an electric current because what more is a current than just electrically charged things moving around, right? So now the ions that have positive and negative charges, this might have a positive charge, this might have a negative charge, this might have like a positive 2 charge. There's ions moving now because those channels open up, and now there's an electric current. So you definitely have to supply current for that, or you have to supply energy for that current to work because your muscles are essentially, or not your muscles, but your that neuron up there, that top neuron that's giving the transmitter out, it's essentially acting like a battery because it's supplying current. So there still has to be some energy for that electric potential energy, or to make electric potential energy to the battery to make a voltage difference, which drives the current. Um, However, these are often modeled like springs. These ion channels. So when they're opening up, these experience some force. These experience some force, basically, and they're often modeled like springs. We're ignoring the signs here. Actually, I'm not going to ignore the signs. They're slightly revealing and slightly important. Um, these are often modeled like springs. So this is F equals negative kx. X is negative, so F is pointing. Yeah, displacement is this way, so F is pointing this way. And for the same case here, we have negative F is equal to kx. Those are just there. Those are equivalent statements, but one of them is revealing about the sign of F. So they're being pulled apart, and that actually does have some elastic potential energy. And although a lot of the chemical potential energy gets turned into, or although the electric potential energy, most of it gets turned into potential electric potential energy or electric potential energy, chemical potential energy. I always forget that. I always mix them up. Um, the energy that's exerted by or released by pulling the ion channels apart, you still need energy for that. Um, so your body's still doing something like physical. It's just the physical thing, the physical work is not from pulling on the box. It's from your muscles actually contracting. They release some energy. Let's look at the graph here. We have F equals kx. So therefore it's linear in F, and we already established that's the area. So this is 1/2 base times height. The work is 1/2 base times height, which is 1/2 F times x We know F is kx, so that's 1/2 kx times x, which is 1/2 kx squared. So that's a measure of how much energy is released when those ion channels are opening up, assuming that spring model is right. I haven't actually read a paper about it. I've just heard about it in the physics department that I'm under as a student. They model those ion channels like springs. Um, they could be nonlinear springs, in which case I couldn't show you the formula without calculus for the energy that's exerted. But this is essentially potential energy stored in the spring. And if potential energy is lost in the spring, the energy is released, so the body has to keep on supplying it with more and more energy. So you need to eat food. So that's not really a whole lot relevant to physics, but it's good to understand for intuitive calculations that someone will tell you work is a measure of how much energy you exert doing an activity. That's more of a colloquial definition, but the physically your body, your you as a being, you're not doing work on the on the string holding the box. What's actually going on is your muscles or the neurons are doing work almost indirectly on your muscles contracting. So let's see, what else can we do? We'll talk about circular motion. It's very brief. I'll expand the canvas size. So what are some examples of circular motion? Let's think we have a bank curve. Yeah, bank curve's a good idea. So basically we have a car. We'll just label it with a dot, traveling on a curve that turns around, or rather loops in a circle. And the close-up image is some angle theta right there, and the car is right here. So the whole idea is we're gonna try and find the work that normal force does, because the normal force does. We're gonna box this a little bit just to be a little neater. The normal force pushes the car inward, so it should make sense that that does work, right? So what causes that motion? It's the normal force, right? And we're gonna break up the normal force into components. So the normal force pointing outwards like that. And then let's see, we have these axes, or rather, I'll draw the axes out in a different color. That would make it a little more revealing. This angle is also theta, which therefore implies this angle is theta. Some cute little geometry with parallel lines, which implies that this angle is theta. So the normal force that's pointing inwards is n sine theta, right? Because we have sine theta is equal to opposite over hypotenuse, which is normal force in the in direction divided by normal force. So we have the normal force, or rather over hypotenuse, yeah. Okay, yes, we have n in the in direction. It's equal to n sine theta. So I'll make that theta a little better. So we do have an expression for the normal force, and then we can equate these and get n sine theta is equal to mv squared over r. But what's n? N is this component of mg, or rather, is that right? No, that's not n doesn't matter. The deals in n don't matter. I have to think about whether that's those are equivalent or not. So we have this formula, and we can substitute stuff in and do the values with friction, because we know friction is mu times n, which would be what we can divide this over to this side, mv squared over r sine theta that'd be the friction force, but it's not really, like, or rather this times mu. It's not really necessary. When we're talking about how much work the normal force does, the normal force is perpendicular to the direction, right? Um, the note here is that we have this is the velocity vector, and this is the force vector. That's the kind of the definition of a centripetal motion is the force is perpendicular to the velocity, and it makes it move in a circle. And we know that velocity is change in x per change in time. Or in this case, we'll use the notation s because s represents arc length because it's moving. It's moving in terms of arc length, not in terms of a one linear direction, right? Because it's moving in a circle. Delta x would be like a straight line. Delta s is moving in a circle. So we have, therefore, there's no angular dependence on this. So the force between, or the angle between force and velocity is going to be the same as the angle between force and displacement, right? We'll call it delta s because the angle between velocity and delta s are going to be the same because v is just delta s divided by delta t. It's just a scalar factor. So because this is equal to 90 degrees, and the cosine of 90 degrees equals 0, the work is equal to 0. Or rather, this is the work done by the in component of the normal force. So we established that detail. It's kind of very important. They kind of like to trick you on things. One way to apply this is a planet moving in a circle. We have a sun, maybe. So yeah, let's say we have a sun. SUN. I hope I don't have a sun. That'd be bad. I'm only 19. That was a bad joke. So we have some displacement vector. I'll make that a different color. We have some displacement vector. That's not a delta. That is, yeah, we'll just make it all normally oriented. And the force vector, the force of gravity. And one question they like to ask is, um, how much work is performed on that planet um, after it travels half a revolution, which would just mean the planet goes from, let's say, here to here, the area across from, or the region across from the planet, right? Because a period is a full rotation, so a half period or a revolution is a full period. Therefore, a half a revolution is half a period, and vice versa. It's the same case here. The angle we have delta s is perpendicular to the force of gravity. Therefore, the work, which is equals to fg delta s cosine theta, is equal to fg delta s cosine of 90 degrees, which equals force of gravity times delta s times cosine of 0, which equals fg, just going through the full calculation here, delta s times 0, and this is equal to 0. All those terms go to 0. And that's mathematically why the cosine of 90 degrees is 0. Physically why there's no force pulling in the direction of displacement. So the actual displacing isn't really expending any energy just because it's not counteracting any force. It's exactly perpendicular to that force. So that's that explanation. Let's see, what else can we do here? We'll talk about power. We're gonna go back to this, motor unit, motor neuron dendrite thing. So in terms of energy, right? It's kind of doesn't really make sense to talk about energy in terms of an instantaneous rate for something like this, because what's more important is how much energy you're expending per time, right? Because it's just, like things that you eat, they have finite amounts of energy, um, and it would be like saying like, oh yeah, well I did this, my neurons did this much amount of work. If you just talk about that with your friends, my neurons did this much amount of work contracting my muscles. So you like how though? Like the whole there area there is it like if you eat an apple and how much calories are in an apple? Hold on, I got an email from one of my professors. How much calories in an apple? Speaking of that, that man's super sweet. He just emailed me a scientific paper that he thought I'd like, just cause calories in an apple. Okay, so it's about 95 calories. So the what should we call it? We'll call it U, because that's kind of it's a potential energy almost. U equals 95 calories. And if you don't know, calorie is just another unit for energy. So we could talk about this in the same case. A calorie is just a joule times some factor. So this is for an apple. Again, we're just motivating the idea of power here. So when you say like, let's say some process did 95 calories of work in your muscles, how? Like it didn't just all go at once. That wouldn't make sense. It would make more sense to sort of decrease at some rate. So we want to look at the rate something does work at, which can tell you a lot more. For example, if you're exercising, you want to know how much calories you're burning per minute, not how much calories you're going to burn total, because that's not very useful information. It doesn't tell you how long you should work out. So the whole idea here is we have power. We're going to call this power is equal to uh, some change in work per change of time. And the convention here is that work is already it's already a infinite sum, and the infinite sums are sort of they're sort of changes already. Again, I can't really talk about that without some math nonsense. The whole idea here is that this would be the average power. So if we say I used up all those 95 calories in a minute, the power would be 95 calories per minute, um, which is a useful measurement. Also, I just want to worship that G that I drew right there. But I forgot I can't laugh. Okay. So, this is the whole reason there. And when we look at instantaneous power, this is just going to be the slope of work per time. So we have delta. We're going to talk about that a little bit more. We have power and time. Let's say we have some graph here. I'm going to make it a parabola just for fun. It's not really parabola, whatever. Parabola. If only I could speak. So let's say we have the average power from some initial time to some final time. We'll call it 6 seconds. We have some nice. We have some slope there. If only I could draw. Yeah, we have some slope there. And then if we draw it from something a time closer, notice that it's slowly and slowly and slowly approaching the slope of the tangent line at the origin, which would be, or the slope of the graph at 0. It's slowly approaching this value as we get values closer and closer and closer as delta t approaches 0 for the same reason as before. Delta t is just approaching some infinitely small value. So that's why the instantaneous power is going to be the slope of that tangent line at that point, because as delta t gets smaller and smaller and smaller, the slope, or that actually, this would be work per time. The slope of work per time, well, delta w over delta t is the average slope over that interval, and as delta t gets smaller and smaller and smaller, the average slope approaches the slope of the tangent line at the point of the graph. So what we have when we do that, you can have any curve. Let's make it real crazy just for fun. We'll end it with a circle. If we want to construct the slope of a tangent line of something, which is very relevant to AP physics problems, we want to draw a line such that it only just brushes up on the curve. It gets a little more complicated in areas like this because just brushing on the curve means it actually intersects the curve at some point. But it basically means the slopes are equal at that point. And that is actually equal to instantaneous power because the average power, right, we have to define average power over some interval, let's call it 0 to 3 seconds. However, as we approach, let's say we're approaching 3 seconds, that becomes a power over 3 to 3 seconds, that's just kind of annoying to write. That would just be the power at 3 seconds. So that's the idea behind power. And again, the same question arises. What happens to the man in the box up here? His power is also 0. It's still 0, despite intuition. Mathematically, that's just because delta W, it's a constant, so it's equal to 0. He's always doing 0 work, so the work never changes. So therefore, P equals 0. And again, the more physical reason is the reason mentioned below it with the neurotransmitters. So that's that. What else can we do? Yeah, I have a practice set. These are just kind of very mathematically heavy problems, and it's literally almost just plug and chug, I don't really think is worth asking. Oh yeah, derivation for the power equation. So we're gonna look at this a little bit. So we have power is the change in work. We're just gonna call it work for now. Work over change in time, and that's equal to um. Let's see. We have. How can we do this? I'm trying to think. Does this method work? The definition of work, F sub k delta T sub k. Hmm. Yeah, I'm trying to think. I'm trying to think of how to do this calculus and vector math. Basically, what we have here is we have the general formula for power that you might see sometimes. P equals F V cosine theta. Um, yeah, okay, I see how to make it work. So we have first we have work is Fx. We're going to ignore the deltas. Fx cosine theta, and we're just assuming some things are going to be no, no, never mind. We'll just divide both sides by delta t, even though it's not necessarily right. Divide both sides by delta t, and we get power is equal to F cosine theta times displacement over time, and that's V. And we can look back at the planetary motion example. The power is still going to be 0. The velocity is constant, the force is constant. If it's moving in a circular path, but the angle is still 90 degrees. This time we don't even have to make the transition between the displacement vector and this velocity vector. We can just say, look at the angle between velocity and force. There's 90 degrees, and the cosine 90 degrees is 0. It's the same reason before. There's no same physical reason as before. I just cited a mathematical reason. The physical reason is the force of gravity isn't, or the speed, or the thing that's driving the speed of the orbit. It's not being pulled or hindered by any force, so it doesn't have to exert any power to do that. Power is kind of tricky, especially when you see some results that are kind of hand-wavedly explained. Um, but lucky for I think every physics student, power is not really a very commonly talked about thing. Um, you may see multiple choice. It's worth learning, but it's not worth studying immensely. So if you're watching this, you're watching the replay. My Instagram, as I always conclude my streams with, is jjeffries12. You could DM me any questions you have for pretty much any STEM homework. I'm a biophysics major, which means that my thing is kind of is the intersection between physical chemistry and biochemistry. biochemistry looking at the chemistry of biology, and physical chemistry looking at the physics of chemistry. Um, atomic structure, thermodynamics, all that good stuff. So I know math, I know physics, I know chemistry. I sort of know some biochemistry and biology. Um, my voice just cracked. That hasn't happened for years. So you can DM me pretty much any STEM question, and I'll try and answer the best I can. So if you're watching the recording, take it easy. Have a good night, afternoon, and morning, whenever you're watching it, and I hope you learned something. Bye.